Has anyone actually seen Mir since I've seen him? So he's still alive? Because I got an email from him saying he's studying at home.
Yeah, he is.
For real?
Yeah.
I suppose. It's not going to be great for his visa though, but...
Yesterday was downstairs, I was smoking and he was coming to the light.
He was on campus?
After he came,
And he didn't come by to say hello to me?
no, you were home by the time.
Oh, okay. Good sandwich.
If he came to the office, you would kill him.
I know, I wouldn't kill him much.
I'm not mean only you, only teacher.
Who's his chemistry teacher? EAP? Maybe he'd get a hard time from Connell. Connell is his course leader, isn't he? So
Yes.
Half-Life, not the game. Unfortunately. Quite a straightforward lesson, in fact, quite straightforward. Only one formula for it, not that many slides, so we'll easily do it today, easily. Okay, do you want to maybe open your notebook? Half-Life is the name of the lesson.
Really?
Yeah, really. It's just like the game.
I thought you were talking about me.
Half-Life, Mir.
And then you wouldn't die all the way.
Okay. It's loading. Half-Life. So we know that n equals n0 e minus lambda t. We have this formula. And we also know what the graph looks like for this. It is like this, which we did in math class, so that's all fine. What's interesting about this graph is that the time required for half to decay is the same no matter when we start looking at the sample. So, impossible. This couldn't be. We thought you were Mir. Look how disappointed they are. Yeah, that's crazy talk. What do you do?
I just have a very small problem down
Do you? Is it on the projector?
Man, 2 seconds.
One moment. Projector problem?
Yes.
نفس الحنكة هذا ثاني جبنة عايز الجبنة لا هذا مستحيل هذا هو خل ايش زي الميتة ايش زي الميتة liters. These are nice. والله أنا ما أقدر أمتحن يا مان، أمتحن ممكن على لسه طوالي.
موافق؟
أي. هذا النهاية. موافق يعني مش كده.
لكن هو بعد اللي بتكمل.
والله أنا موافق إنه أنا أمتحن.
بعد ليه؟ درس كل حاجة؟
مش دارس كل حاجة، أنت لازم تكتب. لأنه لو عشان اللي قدام حبقى درسته زمان حبقى عندي لسه درس قدام. ودرست جديد أكون أصلا يعني ما عندي طاقة عشان أقعد له تاني.
يا مان الإجازة بيتعمل إيه في البيت؟
الإجازة ما كانت في التشكيلات حاول أعمل فيها كيمستري. وأنا عندي تيست المفروض أمشي أعمل بدايتي.
والله؟
عشان يقولوا
لا يا دور.
يومين تيتوريال ويومين تيست. يعني أصلا مو كل أسبوع، أنا 3 أيام أصلا بس.
في البريك بس أنا بقول
حياة عادية يا عظيم. لسه لو لقيت امتحان بعد اليسر الصبح الثاني لسه ما هي احنا بقعد بقرا كده أمام بنفسيات بالبيت. يعني أنا بدرعها يزار والله. يعني هسه عندي لسه لو محمد لسه ده من لسه كده مرجع على الرجل.
He couldn't get the projector working. It wasn't plugged in. True story.
Wasn't plugged in?
True story.
Okay.
Plugged in?
No, plugged in the VGA. The
HDMI.
Okay.
yeah. Fair-ish.
Not bad, yeah.
It is a bit. Right, so some data to make what I was saying clearer. So if you were to, let's just load it up here. Oh, it's loading, sorry. Not too far. There we go. So, let's have a look at the time here. So, at the very beginning, how many moles did I have? 100. How long until I have only half the amount of moles of this radioactive material left? 2 seconds. Correct? Because it takes 2 seconds to go from 100 to 50. Now forget about the 100. Let's start again. Let's say I start at 50. How long until I have half that amount left? 2 seconds again. Do you see what's happening? Every time 2 seconds has passed, it's halved. Regardless of how much you have at the beginning. It'll take 2 seconds to half whatever you have. So this is the concept of what we're coming into next called half-life, which is the time required for half the sample to become radioactive, to become stable.
Become stable?
Yeah, in other words, for non-radioactive, half of the radioactive substance to decay. So, of course, what's the unit for half-life here? Unit seconds. Yeah. You're still writing, yes? Okay. Continue?
Yeah.
Yep, okay. Now, we have a formula for calculating the half-life, but I want you to try and figure it out, and then I'll do it. It's not that difficult to do. I'll get you started on it. So we have one formula already. Activity equals activity 0 E minus lambda T, or the other one, N equals N0 E minus lambda T. Both you can use for this proof. Let's use this one. So I want to know the time until, 2 L's in until, isn't there? No, that was wrong. The time until half remains. So the time until N equals, what would you say? Half N0, very good. Half N0. So if you substitute that into this and solve, you can get a formula for the time. And that's what I want you to try and do. Try and solve this for time. You got the idea, Mishri? Yep. Got an answer? Excellent. What did you get for T? Half what?
Minus into over. No, into over lambda.
I believe so. So we have a half
Yes, same.
N0 equals N0 E minus lambda T. The N0's cancel, and we can put a log on both sides to cancel the E. So we end up with log a half equals minus lambda T. So the T will equal minus log a half over lambda, which is minus log 2 minus 1 over lambda, which is log 2 over lambda, as you said. Because this is a special time, we write it like this, T, and we put a little half here for half-life time. And in the formula book, they actually write in log 2 as a decimal, which I think is 0.69, although I don't remember. But this is more accurate, of course. And you got this. Good job. So the formula here for half-life is log 2 over the decay constant. Let's have a look at that. Now, the only reason I wrote it like this is because probably in the formula book it might be written like this, but I don't think it's quite useful to write it like this. But anyway, it's the same formula as what you just found there. Half-life time is log 2 over lambda. Okay, continue. You got this formula? Great. So let's do this one together. The isotope, carbon-14, has a half-life of 5,730 years. What is the half-life in seconds? What are you shaking your head for?
Its half-life
Yes?
500.
5,000?
5,000.
730 years.
Times
365. Times 24 times 3,600. Give me the A answer, please. I'll open up my calculator too.
Immortal.
What? Well, compared to humans, yes. It takes a very long time for carbon-14 to decay.
You don't need the time. You need the into over the decay constant.
No, for the first part I said, what is it? Oh yeah, what's the half-life in seconds? So, that's the half-life there, 5,730 years. I just want it in seconds. You understand me, sure?
Is it 1.5
No, just go 365, it's fine.
times 1.8 times 10 to the 11 seconds.
Yeah, should be a really big number. Yeah, you got that?
Multiplied by 24, 365.
Yeah, it's this here. I'll write it down. Here for you. So, what did I say? 5,730 years, was it? Yeah? Okay. 5,730 years. That is 5730 times 365 times 24 times 3,600 seconds. And you got E at, what was it? 1.11? Yeah. Okay. Do you have a calculator? Of course you do. I can give it to you? Okay. So, the B part now. What is the decay constant? So calculate that, please. Should be small. Let's have a look. So, did you say decay constant is log 2 over this half-life? Yeah. So that's 1.8 times 10 to the 11 over something like 0.69 roughly. What did you get, did you say?
Yeah, isn't it?
Oh, sorry, I have it upside down.
It is log 2 over 1.8 times 10 to the 11.
Oh, I wrote, yes, I understand. I wrote this upside down, yeah. So that is 0.69 over 1.8 times 10 to the 11. And what did you get?
3.85 times 10 to the minus 12.
Yeah, that seems good. Okay, C. The molar mass is 14 grams. How many moles are in 100 grams? Yeah, what you get? Sounds right. 100 over 14, so 7.1 moles. Oh, sorry, yeah, why did I write 17? 7.1 moles. Okay. You start off with 100 grams. How long until you have only 25 grams left? Okay, you have all the numbers you need, so calculate that. You want to go from 100 grams to 25 grams.
What was the constant?
You gave me it.
Yeah, I did like.
Oh, right.
M equals 100. M0 equals 25. The other way.
M0 is 100.
M0 is the other way. So 0.4.
Don't want to calculate that now? Don't want to calculate? Go on, answer. Give it to me in years, of course.
Wait, 25 over 100 is 0.2. 0.25, that's it. Well, that's okay. 8 over 2.8.
Big or small number?
No. Minus it's wrong.
Minus number?
No, it's 0.000 something. This is the second time we do this.
Yeah, we had this trouble earlier too.
Yeah, I don't know why.
Maybe Musharif's bad luck. He's sit beside him.
25 equals 100 times e to the power of minus 3.85 times 10 to the minus 12.
Yes, result's good.
Log 0.25 because 25 equals minus 3.85.
And put that all over the decay constant. Now don't press the divide button, use the fraction button in the calculator.
Log 0.25 over 3.85 minus.
Yep.
85 minus 12.
Big number now?
Yes.
Divide by 3,600 to make it hours. Then after you get the answer, divide it by 24 to make it days. Then after you get that answer, divide by 365 to make it years.
Still big.
Yep, should be. What you get?
11,000.
Sounds about right. Sounds about right. Now, you did it the wrong way, but you got the right answer. The reason I let you do it the wrong way is because you'll now appreciate the better way of doing it. You start off with a full amount of 100 grams of carbon. Then, after, what's the half-life? 5,730, is it? 5730 was the half-life.
Yes.
Years. Was it? Yes? Can you check?
Yes.
5730. So after 5730 years, how much do we have? 50 grams. Now, after 5730 years again, how much do we have? 25 grams. So the total is just 5730 plus 5730. 11,460 years. Is that what you got? Yeah. So I did that on purpose so you'd... very often in the exam, students fail to see that what they are trying to get is a multiple of half-lives. So 25 was 2 half-lives. That's what I wanted you to now see. Now in the last part E, I say how long until there's less than 1 gram. Now 1 gram is not a multiple as a half-in of 100 grams because it goes 100, 50, 25, 12 and a half, so on. But I think it's reasonable if you approximate. I want you to keep half in your 100 grams until you get to something which is about 1 gram. But please note, I specifically said, look, how long until less than 1 gram? So keep half in until you have less than 1 gram, and then count how many half-lives that is.
7.
Is it 7? And what are you left with then?
0.7.
Of a gram.
Yes.
So 7 half-lives. So do 7 times 5,730.
40 and
40110.
40110. 40,110 years. So the answer is about 40,000 years. Oh wait, 41 or 40? 40, yes,
No,
okay.
no, no.
Musharif.
Sorry.
Thank you. You okay with this now? Yeah, 40,000 years to go from 100 grams to 1 gram, with less than 1 gram. Yeah. Oh, yes. Well, for our purposes, there's not really a difference of 40,000 years and 40,100 years because it's still on a scale beyond measurement.
Well, it says less than 1 gram, so it could be anything.
Yeah,
Could be anything, it's only that so close.
4,000 and more.
Yeah.
Yeah. 40,000 years.
So I can use the half-life trick either way.
Probably in the exam I wouldn't use it for this question because I would definitely use it for the previous one because you get bang on the right amount.
Yeah.
But here I'm just doing this as a demonstration of a quick approximation for calculating time without having to use the exponential formula. So it's the reason I did it was to show you that, to give you a sense to estimate answers. So like if I said, I'll give you an example. If I have 100 grams and I want to know how long until it's 20 grams, well, how many half-lives is that?
1, 2, 3.
Not quite 3, not quite 2. Is it 2 half-lives? I'd be at what? 25. 3 half-lives, I'd be at what?
12.5.
So is it closer to 2 or 3? 2. So is it more or less than 2? It's a bit more than 2 because it's not exactly 2. So I would estimate the answer being like 12,000 years, a little bit more than 2 half-lives, you know. And that way, if you actually calculated and got an answer of 12,200 or whatever, then in the exam you know you have a reasonable answer. Yeah. Yes.
The exam, a roughly answer accepted.
A what?
Roughly answer.
Now, as I was saying to Ian, I wouldn't do it this way in the exam. I just did it this way to just get you to learn the importance of estimating.
Do it to make sure.
Do it to make sure. However, the way I did D is fine for the exam because it's exactly 2 half-lives. Yeah, okay. Right, let's have a look at some questions for homework here. Loading, crashing. Okay, here we go. We'll do this question now. In fact, these questions are quite short, so if it takes you 5 minutes to do this, I'll do the answer, and then we're finished another lesson. For example, the first one we could even do it in our head. Radon 222 has a half-life of 2.8 days, and you start off with 25 grams. How long until less than 1 gram? So let's estimate it. 25 becomes 12 and a half. That's 1 half-life. Then it becomes 6 and a quarter.
Yeah.
That's 2 half-lives. Then it becomes 3 and an eighth. That's 3 half-lives. Then it becomes something 1 and a bit, and then it becomes less than 1. So 5 half-lives is what I reckon. 5 half-lives. 5 times 2.8 is 14 days. So the answer for part A is 14 days. So they're quick questions. So why don't you just try and finish these now in 5 minutes, and then we'll do the answer. So I've already done the first one. Oh, sorry, you wanted how long? What is the decay constant? Is next. B is the decay constant. The half-life I give it to you, 2.8 days.
So I use 2.8?
Yeah, of course. Or you can convert it to seconds. You can leave it as days, but just remember all time will be in days for the question then.
Done by day,
2.8 times 10 to the minus 6.
Days or?
Decay.
Yeah, per day or per second? Per second, okay. So I'll do this in days just for kicks. So the lambda equals log 2 over the half-life. which will be 0.69 over 2.8. Can you tell me what that is, please? 0.25, we'll say. 25 per day instead of per second. Okay, C now. What is the initial activity? And also I give you the molar mass is 222 grams. And remember, I tell you that 25 grams is what we have at the start. Got an answer? So, okay, sorry, there you go. Got an answer there, Adnan? Guys, got an answer? Yellow what? Got an answer?
1.89.
Yeah? It should be. Hang on, let me do it now. So we should use the formula A equals lambda minus lambda n. And we know the lambda. Now I'm doing mine in per days. It doesn't change how you do it. So I'd have minus 0.25 per day. But you would have a much larger number here, wouldn't you? Because you're doing yours in seconds, yeah. Now, I hope what you figured out was how to get the n, which is the number of atoms, which is Avogadro's number times the number of moles. How many moles do we have? Well, I said we had 25 grams of radon and the molar mass is 222. So we have roughly 0.1 moles. So, if I just hit this in on the calculator, it would be Avogadro's number, what is that, 6.02 times 10 to the power of 23, times 25 over 222. Now, my activity will be different to yours because yours is equals per second, whereas mine's per day. So my answer should be like 10,000 times bigger than yours. Huh? Yeah. 1.69 times 10 to the 22. 1.69 times 10 to the 22 atoms per day. Now, if you want to know if your answer is right, I'll convert this into per second. Yeah. So let me just divide this by 24. Did you get an answer like this?
Almost.
Oh yeah. Well, what you got?
898.
Oh yeah. Well, there's round in here. 10 to the 17 though.
Yes.
Then it's fine. Yeah. Okay. D now. how long exactly until there's 1 gram left. So previously we estimated this as 14 days, but let's calculate it exact. So we have 1 gram is what we want, and we start off with 25 grams, e to the minus lambda t. So this works out to be log 1 over 25, which is 0.04 over, and in my case it'll be minus 0.25, because that's what I'm using for my decay constant. So log 0.04 divided by 0.25, and I got about 13 days, which isn't too bad, 12.88 days. Okay, and then lastly here, E, what is the density of radon in the room when there's 1 gram present? And I give you the size of the room, it's 20 by 30 by 3. So what's the formula for density? Yeah, so density is mass over volume, which is 1 gram over 20 by 30 by 3 is the size of the room. So that will be a very small number. Very small. 5.56 times 10 to the minus 7. Kilograms per meter cubed. And finally, what's the molarity of radon in the room? So do you remember molarity from chemistry? Yeah, I'm sure there's another way to do it. Molarity is CV, or C over V. Anyways,
N equals C, N
molarity is just basically the number of moles over the volume. It's a density of sorts. Did we work out how many moles is 1 gram? No, we didn't. We need to do that. But we did work out the volume. 20 by 30 by 3. So we need to work out how many moles there are. So that would be 25 divided by 222. This is the molarity. The unit is m, moles per liter. 0. You think the final answer is?
No.
Moles.
Yeah, 0.11. Yeah. Divided by 20 by 30 by 3. So get a very small 6.26 10 to the minus 5 moles per liter. Do you have a letter you use for molarity in chemistry? What do you use?
No, molarity is concentration, which is molar.
Molarity is concentration. What letter do you use for concentration? Big or small? Do you use square brackets? I usually see it like this, square brackets.
Yeah,
This means concentration of radon. Yeah, okay. Oh, I'm so sorry I kept you 1 extra minute. Forgive me, please. What class have you got next? That was the last question. Group tutorial. Are you going to make it to group tutorial this week? I think last week when you tried to get to group tutorial in A401 after physics in B401, I believe some of you couldn't quite make the journey to the next building. Yes, it was a horrific tale of woe. Anyways, I don't particularly care. My worry is just physics and maths, and trust me, that's enough of a worry. I don't need to be worrying about your chemistry and group tutorials and EAP. Okay, so good news is, because we got this homework finished, there's no homework for this, and you can see that the lesson wasn't that difficult. So what we'll have a look at next time, I think we will be at graphs of activity. No, you'll have to wait for that lesson. You'll have to wait for that lesson, I'm afraid. Just like how you have to wait for Kepler. Dude, wait. And if you really can't wait, if you can't contain your excitement, you can go to my YouTube channel and watch the video from last year.
So there is it.
It is there, on YouTube, from last year.